Okay, let's begin. Hello, everyone. My name is He Xin, software engineer in ByteDance. Today, my colleague Hong Hao and I will give you a topic about the challenges of building AI infra on virtualization. Here's today's agenda. The first part covers the problem of building AI infra on virtualization. And then we will introduce our design and implement to resolve the problem. And the third part involves the future work. Okay, let's begin the first part. The PCIe communication efficiency between GPUs or GPU and NICs is crucial for large-scale model training and inference. But in virtualization scenarios, there will be a serious performance degradation due to the enablement of IOMMU. And the other problem is that due to the frequent PIO and RDPMC operations, there will be a high number of VMEXITs. The next part, I will introduce our design to improve the PCIe communication efficiency that we call this solution direct P2P. This figure shows the read or write TLP transmission path when disable IOMMU on host. Now, because the TLP carries the HPA and the NIC can read or write GPU memory directly. When we enable IOMMU and the GPU and the NIC are both passed through into one VM, now the TLP will carry the IOVA and it can't be routed by switch directly. The switch will redirect the TLP that carries the IOVA to root port, and the IOMMU will translate the IOVA to HPA. After this, the switch can route this TLP directly. So that we can see now, due to the enablement of IOMMU, the transmission path of the TLP has been changed. In addition, that the switch relies on the access control service to redirect the read or write TLP and the read compilation TLP to the root port. Now I will introduce the main control bits of ACS, such as request redirect and compilation redirect. If these bits are set, all the TLP, such as read or write and read compilation, will be redirected to the root port by the switch, and the direct translated bit will be introduced later. So due to the transmission path has been changed, that there will be a serious performance degradation, and the write and read speed has been reduced from 196 to 121 and 170 gigabits per second. So to avoid the performance degradation, that the NIC in VM can support ATS capability, like this process. Our purpose is that the transmission path of the TLP for the device without ATS in VM is the same as the transmission path in host disable IOMMU. So if the switch can route the TLP directly, the TLP must contain the HPA. And if the NIC with ATR supported has a local cache, that's we call it ATC. So let's look at the process. Initially, the ATC is empty, and if the NIC want to read or write some data to GPU memory, first it will send a TLP request. That we call this request address translation request, and this request will also be redirected by the switch to the root port. And the IOMMU will receive this request and translate this request, will translate the IOVA to HPA. So after translated, it will respond a TLP to the NIC. the NIC will receive this response and store the LVA to HPA mapping into its local cache. Now, with the local cache, the NIC can send a TLP that carries the HPA. A special thing for this TLP is that its AT field is 10. So now we can see that we can get a TLP that carries the HPA and its AT field is 10. But for the switch, how does can identify this TLP should be redirected to the IOMMU, or this TLP carry the address can be routed directly? So now we have mentioned about the direct translated bit of the ACS will be used. If this bit says, the switch will check the AT field. The switch will check the AT field of the TLP, and to determine whether the TLP contains the HPA. If the direct translated bit is set and the AT field of the TLP is 10, now the switch will believe that the TLP carries the HPA and will route this TLP directly, regardless of other ACS control bits such as redirect request. So through the above method that we can see, for the device with ATS supported in VM, the transmission path is the same as the host disable IOMMU, and the performance is also the same. Okay, like this. So now we have introduced the transmission path of the TLP when disable IOMMU in host, when enable IOMMU in VM without ATS and with ATS. So our problem is that for the device without ATS in VM, is it possible to ensure that the transmission path of the TLP is the same as the host disable IOMMU and with ATS supported in VM? Like this. We want to ensure the transmission path is like this. So there will be two questions. The question one is that how to get HPA without IOMMU, because now the switch, because we want the switch will not redirect this TLP to the IOMMU, so we must get HPA without IOMMU. And the other question is that how to avoid the ACS redirection, such as read or write and read completion. For question one, normally we need IOMMU to translate the LVA to HPA like this. But there may be a corner case that the translated address HPA is equal to the address LVA like this. So maybe now the switch can route this TLP based on the LVA address directly, because now the LVA is equal to HPA. For question two is that we just need to disable all ACS control bits to make sure that the TLP will not be redirected to the root port. Let's look at the detailed design. Okay. Our purpose is that for the device without ATS in VM is the same as the host disable IOMMU and with ATS supported in VM. As mentioned above, when the LVA is equal to the GPA, the switch can route this TLP based on the LVA address directly, so that we can get this transmission path. And another thing we need to do is that to disable all the ACS control bits. So now the switch will not redirect the read or write TLP and read completion TLP. It will route all the TLP based on the address of TLP directly, regardless whether it's HPA or LVA. So that we can see that about method that to ensure we will get this transmission path that we modify the VM BIOS to ensure that the GPU bug address space in VM is the same as the address in host. And another thing by this, now the for example, when the NIC want to read or write GPU memory, and now they are in the same VM, the NIC now receive some data from other host and want to write this data to the GPU memory. Now the destination of the write TLP is the GPU bug address in VM, because now we have modified the BIOS to ensure that the GPU bug address GPA in VM and HPA in host are equal. So now the switch can route this TLP, TLP based on its HPA address, and the TLP will correct. Here's through the direct P2P solution that we can see that the read-or-write speed is the same as the host disable IOMMU and with ATS supported in VM. In addition, if we want to use the direct P2P solution, we must pass through all the devices below one switch into the same virtual machine, because if the different device is passed through into different VM, and now we have already disabled the ACS, there will be some transmission wrong. Another thing we need to do is that the P2P solution can only impact the transmission path of the P2P transmission. For the DMA transfer to read or write the system memory, it will not change. The transmission, it also needs the IOMMU to translate the LV to HPA like before. Another thing is that because we have modified the BIOS to ensure that the GPU bug address GPA is equal to the HPA address. So some operations in VM, such as PCIe rescan, will maybe change the GPU bug address. So we must check this situation, that if the GPA is not equal to HPA, we should do something, such as pause the VM to ensure that the GPA must equal to the HPA. Okay, my part is all. It's up to Hong Hao.
Okay, thanks to Hexin. Hello everyone, my name is Hong Hao, and now let me introduce our work on high precision monitoring agents. In our internal AI large model tasks, we often need to get some info to detect bugs, which may rely on high precision monitoring agent. And these agents will read the PCI config space data and use perf to capture some useful information, or connect memory bandwidth, which will cause a large number of VMEXITs and user space exits because of virtualization, just like the orange line in this picture. First, let me introduce PCI port IO case. For example, in I440FX case, PCI config space read, which perform as PCI port IO, will cause large number of VMEXITs and user space exits. Usually, when PCI config read includes two steps. The first is VM writes to IO port CF8. The VM writes the BDF number and offset of the device it wants to read to the PCI host bridge config register via the IO port. Then it calls a VMEXIT. KVM captures the IO port write and then determines that it needs to be handled by QEMU. So the vCPU thread returns to QEMU user space. And the QEMU write the data to the emulated host bridges config register, then return to kernel space. After that, KVM perform VM entry, and the IO port write finished. The second step, we will read the IO port CFC, also causing a VMEXIT. KVM capture the IO port read and it determines that it needs to be handled by QEMU. So the vCPU thread will return to QEMU user space again. QEMU emulator reads PCI config data based on its host bridges config register, which we writed. Then QEMU returns to kernel space and perform VM entry. And this PCI space read data finished. It takes more time than physical machine, especially in QEMU offload scenario. We have implemented an optimization solution that uses memory to cache on the KVM side to accelerate the VM's PCI config space read operations. For the first time, PCI config read, we cache the CF8 write as a key to the KVM, and the CFC output read needs to do another two steps. One is update the CF8 key to QEMU. Another is cache the real value in KVM with the key. After that, we cache the BDF with offset and the corresponding data in KVM as key value pairs. Then we read corresponding PCI config space data will cost less time because we just need to fetch the value in our cache in KVM. No need to return to QEMU user space unless the cache is invalid in some low frequency situations such as reboot or the device hot plug. After optimization, we found that operations like list PCI have cost less time, which 1,000 times of list PCI reduced from 28 seconds to 10 seconds. And now let me introduce our work on PMU pass-through. First is core PMU pass-through. When the virtual machine start up, we stop the CPU PMU's perf event on the core and restore it when the VM shut down. And we pass through the core PMU related MSRs to the guest, allowing it to directly read and write control registers and counter registers. Additionally, for NMIs generated on the host, we check the PMU's global status in KVM. If it's in an overflow state, we inject it into the guest and mask the NMI at the software level. When the guest acknowledges the overflow state, we trap the PMU's global overflow control MSR and then unmask the NMI. And the second is on-core PMU virtualization. We've used the Pyrovert to pass through the host's on-core PMU to the guest. For example, with Intel SPR's IMC PMU, the bare metal implementation uses discovery devices to get on-core PMU configurations information. We use Pyrovert shared memory to directly pass through this information from KVM to the guest. And the IMC PMU on SPR uses MMIO access. So we need to reserve a guest address range for it and set up GP to host MMIO mapping in EPD. A key limitation of on-core PMU pass-through is that it is digranularity, which causes difficulty to share among multiple virtual machines. Our future work includes two parts: upstream and resolve H2D and D2H virtualization degradation by DMA divert. And that's all. Any questions?
Have you looked into the recent work with Intel and AMD, also Google on the pass-through PMU?
Yes, I know.
Yeah.
When we implement our work, we have not found the patches.
Okay.
Yeah.
So that's good to follow, right? So it's good to know that you like to use the PMU, right?
Yeah.
And also for Uncle, basic question is there any use case you want to use Uncle PMU in the VM?
Yes, we want to capture the memory bandwidth in VM. So we currently it is not realized. So we use the Uncle PMU pass-through. Yeah.
Okay.
Thank you. So I have one question. Initially, for ladder, you bypass the ACS, right? So when you said if the GPU bars is not what you actually expected, what are you going to handle? How are you going to report to the guest?
You mean how the VM knows the GPU of the device?
Yeah, because you basically force the GPU.
Yeah.
HGA, right?
We get the info in QEMU, and we use firmware config to pass through it to the OVMF, and we will modify the GPA in OVMF. Yeah.
Yes, but what if the guest modify that?
So it is a good question. We must forbidden these cases.
But what if that is a valid case?
What case?
Yeah, if, for example, Windows will modify the bars.
It will be a future work. Yeah.
Okay.
So two comments. First is on the first part where you talked about pinning the bars to the same physical address, or to passing the real physical address of the bar to your guest as a guest bar. We have patches pending that should go upstream in the next few weeks to basically achieve the same thing in CBIOS, EDK2, as well as QEMU, to basically do full segment population, like the whole topology, pre-populate that from user space already, from the VMM, in that way, not touch any of these of the bar mappings in initialization, which for the Linux case is safe. For Windows, screw them, whatever. The GPU acceleration case plus Windows is pretty much marginal, and nobody cares, right? You don't need peer-to-peer DMA with Windows. So which means let's collaborate, right? You have a solution. Maybe based on what you said, it sounds like you're effectively passing only the individual data into the guest, which is our old approach. That one does break often, so don't do it. Let's agree on the new path, or on any path at all. The second one is the port I/O acceleration. Cool. Great to do acceleration in KVM. It's just for this particular use case, it's the wrong path. The PCI config space access, the main reason why you're seeing so many PCI config space accesses is because Linux is not optimized for the virtualization case and always uses legacy port I/O when it accesses the lower end of PCI config space, even when you use PCI Express, because with PCI Express, in theory, you would just have a memory view of config space that is exactly 4K, conveniently a page, right? That you could effectively one-on-one map as just memory into the guest. So with eCam and a guest that behaves sanely instead of what Linux does, you would be able to just have PCI config space be effectively free. which is the direction we should rather go towards. And that way your number doesn't
maybe-
go half, your number goes to 0.
Maybe our work is currently used in our internal, and that is a good question. Like you say, PCIe will use 4K config space, and that will be a future work. We think we should. For example, we need invalid the cache because when the MMIO.
You don't need a cache if you also take ownership of the guest kernel, which I think in your environment is a sensible assumption. We can follow afterwards. It's fine.
Okay.
I have a rather naive question. How do you get the bandwidth between the network and the GPU, this P2P memory bandwidth? How do you measure that?
RDMA perf test.
Okay.
It's open source.
Okay, so that's all. Thank you.